والسلام على محمد وعلى الطاهرين. السلام عليكم ورحمة الله. Mr. Ahmed, Mrs. Zainab, Mrs. Maryam. Please tell to your friend in Telegram to come in the class. Or I say them, excuse me, are in the Telegram now. Groups. Okay, I said in the Telegram group. That's right. اللهم صل على محمد وعلى محمد. أحسنتم. In this, we are in the transforms. Okay, we said about discrete Fourier transform, then said about discrete cosine transform, and then said about Walsh transform and Hadamard transform. Okay, but this discussion wasn't complete, and we complete them. Okay, we start here from Walsh and Hadamard transform. Again, review. Why you are disconnected? Are you in the class? Please type 1. Mr. Ahmed, Mrs. Zainab, Mrs. Maryam. Do you hear me? Mrs. Zainab is come back. What was Mrs. Zainab? Mr. Oh, what about your Mr. Ahmed and Mrs. Zainab are coming back, but Mrs. Maryam isn't in the class again. That's right. What was about? Your net is weak. Oh, you are in Iraq, Ms. Ahmed, you are in Iraq or in Iran? Mr. Ahmed, are you in Iraq now? Okay, that's right. That's right. Okay. The Walsh transform and Hadamard transform. I repeat for you. We said about Walsh transform that we said we transfer all of the numbers from decimal to binary form. Okay, for example, as bn minus 1, b1, b0, etc. in binary, and you see x and u are represented in binary. That means all of them are 0 or 1. Okay, this is the binary format. And for example, suppose fx has 8 samples and 8 is 2 powered by n. We said in this Walsh transform number of n should be a power of 2. Okay, and then for example we can we show 6 as 1 1 0. Okay, or for example 8 as 1 0 0 0. Okay, this is a binary format. Then that means in 1 1 0 b2 is 1, b1 is 1 and b0 is 0. Okay, here WU in Walsh transform. Salam, Mrs. or Mr. Dalal. Mrs. Dalal maybe. سلام الله يتقبل طاعتكم كلا جميعا. Mrs. Dalal, Mr. Ahmed, Mrs. Zainab and Mrs. Maryam. WU Walsh transform 1 over n sigma over x fx pi minus 1 powered by bi x bn منهای 1 منهای I u. Okay, on equivalent form we said, and this is the T, the transform kernel. Okay, T is this item. That means T minus 1 powered by sigma and f is 1 over n, again sigma. Okay, both of them are 1 over n. This time we see that T inverse is T, not for example NT, and is very better. Okay, but W is 1 over n sigma over x sigma over y fx of y again pi minus 1 bi x bn منهای I منهای 1 منهای I u plus pi bi y bn منهای 1 منهای I v. Okay, or f is 1 over n sigma v and sigma u and sigma v. W u of v again the pi. Okay, we add this. You see here in the two domain Walsh transform contains the kernel value T contains only 1 and minus 1, and both of them are the same. T inverse is T. Okay, and there isn't any here into the signals. The forward and inverse Walsh kernels are identical. That means T inverse is T. Okay, but properties of two-dimensional discrete Walsh transform. About the properties, the concept of frequency exists also in Walsh transform basic functions, as in discrete Fourier transform, as in discrete cosine transform. Okay, the concept of frequency, we can think of frequency as the number of zeros or zero crossings. Okay, or varyings. Okay, or the number of transitions from positive to negative, from 1 to minus 1, 1 to minus 1, okay, and vice versa, from minus 1 to 1 in a basis vector. And we call this number frequency or frequency. The rate of variations, okay? More weight, more frequency, more frequency, more rate. For the fast computation of the Walsh transform, there exists an algorithm called fast Walsh transform. We had this. This is a straightforward modification of the FFT. As you know, FFT is more or better than DFT. FWT is better than WT or DWT. Okay, and you know that for FWT, as for FFT, then your numbers or n should be a power of 2. Here again, for these are repeat. Okay, here is for Hadamard transform. Hadamard transform is very similar to Walsh transform. Again, H Hadamard HUV is 1 over n sigma over x sigma over y fx of y pi over I minus 1 BA IAX BA no BA minus 1 and minus for example n BA IAX BA U for 1-dimensional and this item for 2-dimensional. Salam, Mr. Uday. Ahlan wa sahlan. How are you? That's right. Allah taqabbal ta'atakum. That's right. BIAX, BIAU plus BIY, BIV. Okay, or this item. Sigma sigma f minus 1 powered by sigma, okay, as I say, and inverse f is 1 over n sigma over no x, this should be corrected, sigma over u, and this item sigma over v. Okay, I draw, this is U and this is V. Okay, again from 0 to n minus 1 and again from 0 to n minus 1. HUV again I from 0 to n minus 1, again that item. Okay, minus I plus by BAIX BAIU, not BAI minus 1 MN minus NAU, BIAU, and BIY, BIV. This is the Hadamard transform or 2-dimensional Hadamard transform. Okay, a simple difference here for Walsh transform was BIAX, BN menhaya 1 and menhaya IAU. For Hadamard transform is BIAX, BIAU and BIY, BIV. Okay, for Hadamard. Here. That's right. Properties. Most of the comments made for Walsh transform are valid here. Okay. Salam, Mr. Abbas. Ahlan wa sahlan. Oh, no mushkil. The Hadamard transform differs from the Walsh transform when only in the order of basis functions. Okay, the order of basis functions of the Hadamard transform does not allow the fast computation of it. Okay, by using a straightforward modification of the FFT. That means Walsh transform is better. Walsh transform has FWT. Okay, fast Walsh transform. But here we don't have fast Hadamard transform. Okay. An important property of the Hadamard transform is that letting HAN represent the Hadamard transform of order n, the recursive relationship holds as here. H2n is hn minus hn. That means, for example, if you had h2, you can construct h4 and can construct h8, again h16, 32, 64, and repeatedly, okay? And recursive formula, a simple form. Therefore, starting from a small Hadamard matrix, we can compute a Hadamard matrix of any size, any n, and n of power of 2, okay? H2n, H4n, H8n, etc. Here we have the last slide from the last session was this item: ordered Walsh and ordered Hadamard transforms. Okay, modified versions of the Walsh and Hadamard transforms can be formed by rearranging the rows of the transformation matrix so that the sequence increases as the index of the transform increases. Excuse me, because this is the last slide, I stop sharing and upload the new file. Okay, please be patient. Share document. Browse my computer. DIP. This item. Mr. Abbas Al-Azawi, Mr. Ahmed Qasim, Mrs. Dalal, Mr. Hamid Muhammad, Mr. Uday, Mrs. Sarah, and Mrs. Maryam. No. Okay. That's it. All of you are in the class. Mr. Ahmed, Mr. Hamid, Mr. Uday, Mrs. Maryam, Mrs. Sarah. Are you okay? Mrs. Sarah, Mrs. Dalal, are you in the class? Mrs. Sarah. Okay, I go for the next slides. This is the continue of that file. Hadamard transform, two-dimensional properties of it and itself and inverse, ordered. Okay, this is ordered. I zoom it. Ordered Walsh transform. Modified versions of the Walsh transform and Hadamard transforms can be formed by rearranging the rows of the transformation matrix. Okay. For example, constituting row 1 by row 2, row 2 by row 4, etc. Okay, this is ordering or rearranging the orders so that the sequence increases. Okay, maybe you order a bad ordering and sequential frequency is decreased, but a good rearranging or a good ordering is that tends to increased sequence or increased frequency, okay, as the index of the transform increases. Okay, that means more I, more sequence. That means for I0 you are in DC, for high I's you are in high frequencies. Okay, low frequencies and high frequencies. These are called ordered Walsh and Hadamard transforms. The ordered Walsh Hadamard transforms do exhibit the property of energy compaction. or for compression, okay, energy compaction, whereas the origin versions of the transforms do not. That means for compression tasks, the ordered transform is more better, okay, the ordered transforms, Walsh or Hadamard. This observation is very prominent in the original Hadamard transform, where the basis functions are completely unordered, okay? Whereas in the original Walsh transform, the basis functions are almost ordered. That means Walsh is okay. Walsh, not ordered. Walsh is some okay. But in Hadamard, you should use ordered versions only in Hadamard transform. Okay? Walsh is so-so. For Walsh, non-ordered and ordered may be the same, maybe okay. But for Hadamard, the original version isn't good. The ordered version is good. And we see this item in the last slides, okay? Don't worry. Among all the transforms of this family, the ordered Hadamard is the most popular due to its recursive matrix property. We said Hadamard isn't good. Hadamard versus Walsh isn't good. But ordered Hadamard is very good. Ordered Hadamard is as ordered Walsh, and both of them are good. But this recursive task is very good for us in this recursive property. We could reconstruct or construct H2n from HNs, okay? HN, minus HN. This is very good property and very simple property. That's right. But here, speaking about ordered Walsh transform and ordered Hadamard transform. Here, images of one-dimensional Hadamard matrices. Okay. Here you see a 2x2 Hadamard matrix, non-ordered. Okay, Hadamard matrix non-ordered. But here you see again a 2x2 ordered Hadamard. Okay, in 2x2 you see both of them are the same. Ordering isn't any high performance thing. Okay, ordered and not ordered are the same. But in 4x4, this is a matrix for non-ordered Hadamard for 4x4. Okay, but this item not 2x2. This is wrong. This is 4x4. This is I type here. This is wrong. This is 4x4. Okay. 4x4 Hadamard matrix for ordered. You see the ordering is differed here. Okay. For example, you rearranged Salam, Mr. Ahmed Zahra, Salam, Alam Salam. You see some rows are rearranged, okay? But in the next slide, we see that reordering or ordering is better and has some best or better properties, okay? Go here. More images of one-dimensional Hadamard matrices. This is for 8x8. 8x8 Hadamard, non-ordered. 8x8 Hadamard, ordered. Okay? You see again, an unordered version. This is a better ordered. Don't show or doesn't shown in this slide that what's the best performance. Okay, in other slides we see the better performance. This is the matrix, non-ordered, ordered, and this is non-ordered and ordered for 16x16. This is for non-ordered and this is for ordered. Okay, You see here, in all of them, here, this item is the zero frequencies or DCs, and this item is high frequencies. Okay, we said about the frequency or sequence. This is, for example, U axis and this is V axis. Okay, this is frequency 0 and this is frequency high for U, and this is frequency high for V. Okay, here you see, here is zeros and here is high frequencies. Okay, you see here mass sequences or mass varyings. Okay, compared to this one, here is better. Here is better. Here you see lower varyings in high frequencies, but here you see higher varyings. Here is low varyings. Okay, here is higher varyings. This is low frequencies with low sequences in order. This is high frequencies and high sequences. Okay, this item 16 by 16, this is a complex, a mix. Okay, high sequences for low frequency and high sequences for high frequency, but in order you see a plane and non-sequences for DC, high frequencies or high variations for high frequency. Okay, this is low frequency, this is high frequency. This is the meaning of ordering. Going from frequency 0 to frequency high, or from frequency 0 to frequency high in U and V, you go from here to here, okay, to more frequencies or more sequences or more variations. This is the meaning of or the result of ordering. The result of ordering. Mr. Ahmed said, I'm not Mr. Ahmed, I'm Lom'e. Okay, that's right. Mr. Lom'e, you was with me in the last term semester, okay, with embedded design. That's right. Go for the next slide. Again, you see non-ordered 32 by 32. Okay, this is non-ordered, but this is ordered. Here is low variations in low frequencies and high variations in high frequencies. Okay, this means ordering, or this is the result of ordering. Here for 16 by 64 by 64. Okay, this is not ordered, a mix. Okay, but here you see in DC low variations, in high frequency variations. Okay, or more and more sequences, a more rate of variations. Okay, that's right. But what is the result? Ordering is better or not? Okay, you'll see the results here. Experiment or maybe optional homework in MATLAB, for example. Demonstrate and compare the energy compaction property of DCT, discrete cosine transform, and ordered Hadamard transform. Okay, as for example in this slide. But consider an image of size n by n. For example, you can capture an image by your camera, okay, your phone, and transfer this file to, for example, to MATLAB by image read. Okay. The pixel 0, 0 is located on the top left corner. Okay. You see here is 0, 0 in XY, and here in UV. This is 0, 0. This is NN. Okay. Take a small image patch of size I by I located on top left part of the DCT transformed image. For example, here, this is an image, and this is DCT, okay? And this is, for example, no, this is logarithmic version of DCT. This DCT. The first time you can choose this block or this patch, okay? Maybe all of them is from 0 to 256, okay? And the transform version, this is f(x) of y, this is w or h u of v, okay? This is n by n, and again this is n by n, from 0 to 255, okay? This is the first patch. This is the second patch. This is, for example, the third patch. This is the fourth patch, okay? I by I. For example, 2 by 2, 10 by 10, 20 by 20. That's right. And each time you increase the I by I, you see the energy. And in the last, you compare the rate of energies, okay? Here, calculate this, the density of the image. This is the density. This is the density. Take a small image patch of size I by I located on the top left part of the density transform image. This item, I by I, maybe 10 by 10, maybe 20 by 20, maybe 30 by 30, okay? Here, this patch contains the low frequencies from 0 to I, low frequencies of the original image, okay? We said these items are high frequencies, these items are low frequencies. From 0 to I means low. From n higher I to n means high frequencies, okay? These items are low frequencies. Calculate the fraction of the total image energy, or EI, that is contained on the patch of size I by I. That means when selected this item, you can calculate energy in this item. Where is it? Here, in this I by I, okay? You can calculate EI. Then increasing I, for example, doubling I, again you calculate EI2. And increasing I am calculating EI. Calculate the fraction. Repeat the above experiment for I from 1 to n, not from 0. The smallest one is 1 by 1, and the largest one is n by n. Okay, patch size of that selected image, and you can use and calculate E1, E2, E3 to En. For example, E255. You realize that the smallest possible patch of is of size of 1 by 1. Okay, that one density value only is kept, others are eliminated. The 0, 0 value or DC value 1 by 1 is the DC value. Okay, and the largest possible patch is size of n by n. Okay, all of the items, the entire density image is kept. Plot EI as a function of EI. Okay, you can plot this item in MATLAB. What we see in the next slide. Okay, this is EI, I axis and EI axis. Okay, That's right. Plot EI, repeat the above experiment for the ordered Hadamard transform. The first one was for DCT transform, and we plot EI. Again, we check it with Hadamard transform, and again plot EI. Okay, both of them in one figure. The above experiment is depicted in the following slide here. Here, you see picture, for example, a cameraman. You see it's DCT, and this is, for example, a eye by eye selected picture, another eye by eye, another by eye, and all of them. Okay, this is the logarithmic version of DCT, not DWT. DWT isn't seen in this slide. Okay, you can by this item. Excuse me. By this exercise, you can compare DCT, Hadamard, Walsh, ordered Hadamard, and ordered Walsh. Okay, but here in this slide, you see here DCT and ordered Hadamard. DCT and ordered Hadamard transforms. But see this slide. See this figure. I is increasing from 1, not from 0. We said the smallest one, DCT1 is DCT 1 by 1. Okay, I is starting from 1 to ending to 255. N by N. Okay, and this is EAI. What we see here, I zoom in it. We see that here. This is percent of energies. Okay, for example, 95 hundredths%. Okay, or dot 95 or dot 9. Okay, or 90% of the total energy. This is the total energy for IN. For IN, or a transformation of N by N is a total of energy, total of image transferred. Okay, this is the 100% or 1. 1 is for N by N. But for 1 by 1, you see starting from 75%. 75%. That means a DCT of only 1 by 1. The first item contains more than half of the energy, about 3/4 of energy. Okay, this is very good. Keeping only one item, this is the 1 by 1 contains about or more than, not about, more than 75%. But you see, for example, when you reached, for example, about 20 samples, 20 by 20. Okay, here, for example, 20 by 20, you reach the percentage of 95. That means an error of only 5% in total energy. What did this say to us? Said instead of keeping all of the, for example, 255 items, only keeping about, for example, 20 items is okay. 20 items, or calculating a eye by eye DCT. Not calculating eye by eye DCT, no, this is wrong. you should calculate a n by n dct as this item, okay? Not, for example, 20 by 20 ICT. The n is the same as the original image. And for example, 255 by 255 DCT, but instead of storing or transferring from this machine to this machine a file, you can select and compact and compress, okay, by, for example, selecting about 20 by 20 items, okay, or pixels, from 0 to 20 for U, and from 0 to 20 to for V axis, okay. That means only about 400 items, not a huge number, okay. 255 by 255 is very large number. Okay, this is a saturating curve. That means this item very good, or maybe this item selecting only 40 by 40 patch size, okay. But these two items, the dark, the black and the red is DCT or this transform, and black is ordered Hadamard transform, okay. What is this is saying? This says us this is DCT is better. DCT is better than ordered Hadamard. Why? Because, for example, when selecting, you selected, for example, 21 items, okay, 20 by 20. You see, for example, the percentage of EAI for black or for ordered Hadamard is, for example, 95, but for DCT is, for example, 98. Okay, that means more energy with the same eye. That means DCT is better. DCT is better than ordered Hadamard. And you can select how many items are okay based on your error, your accepted error. Okay, if I select 20 by 20, I have a 5% error. If, for example, I selected 40 by 40, for example, I have maybe 3% errors. Okay. If you selected, for example, 100 items, 100 by 100, maybe you have 1 or 2% errors. Okay. Go to the next slide. Zooming it. What we observed, again, we see in this slide. Obviously, EAI is a monotonically increasing function. We saw here, monotonically increasing, okay? Increasing I tends to increasing EAI. That means more samples, better quality, or more energy, okay, in our file. For a fixed I, the percentage of, here, we can call it cumulative energy function. This curve is cumulative EAI, okay, or cumulative EAI. For a fixed I, the percentage of energy contained in the DCT patch is higher than the percentage of energy contained in the Hadamard patch or ordered Hadamard patch. That means DCT is better. If you selected 20 by 20, the error in DCT is less than the error in Hadamard. Okay, or DCT is the same as the original version. Another one. Here, observe that the DCT curve is located slightly above the Hadamard curve. That means red is better than black. Where was it? Here. Red is better than black, or DCT is better. Okay? For example, by selecting some items, for example 20 by 20, you have less errors in DCT compared to Hadamard. Excuse me. Or in order to keep a fixed percentage of the total energy of the image, you require a smaller patch when you use DCT compared to when you require if you use, for example, Hadamard. For example, you select only 20 by 20 in DCT, okay? But in Hadamard, maybe you use 25 by 25. That means the size of a compressed file in DCT is smaller than the size of compressed file in Hadamard technique. Okay, or DCT delivered us more rate of compressing. That's right. But before continuing, if DCT is better, why we go for Hadamard or for example for Walsh? Because Walsh and Hadamard are very simpler compared to DCT. Okay, very simpler. T is containing only 1 minus 1, on minus 1. That's right. And this is a fast technique. And when we had 2 powered by n, a power of 2 for n for the number of samples, for example, Walsh transform is transferred to fast Walsh transform. Okay, this is one reason of selecting, for example, Hadamard or Walsh instead of DCT. Another one. If the above experiments, you observe that as I increases from 1 to a slightly higher values, for example, from 1 to 10 or from 1 to 20, okay, smaller higher values, the fraction of total energy EI becomes almost 1 quite quickly. Okay, here you see you go from 1 to, for example, 20. You see the percentage of energy is very quickly increasing. Okay, and after some items here is saturating. Some small values, for example 20 value, okay, is sufficient or coffee for reaching a good rate of comparison and a good quality. More I is tending to better quality, but more size of file. This item, for example, 20 or 40. Okay, 40 is a good situation. But for example, this item, for example, 100 and 120 don't have some good differences. Okay, only increasing the size of file, the size of compressed file. Okay, this region is very good. This region, for example, 20 40 or 60, these items have better, good performance, good quality, or a good size of energy rate, okay, and a good rate of comparison, a good small size for or file, okay. Where was, in order to keep a fixed from no in the, oh, okay, here, in other words, the preserved patch contains almost 100% of the energy of the entire DCT image. For example, using 20 number, okay, 20 by 20, this is 20 by 20, almost 100% or 95%, okay, a low rate of error. Don't forget that the energy preservation property. Don't forget the energy preservation property or Parseval theorem. Maybe some of you know. In, for example, in mathematics, okay, or maybe in signals and systems. This named Parseval theory. The energy preservation property, both space x or y and transformed space or UOV domains have identical energies. That means if in here you selected only these items and you reached a 95% of energy in the transform version, in for example DCT version, okay, about 95% of energy is retaining in the original image. After reinversing the transformed image to the original image, only 5% of energy is ignored, okay. And another one, the observation in the previous two slides rely on the fact that both DCT and ordered Hadamard transforms exhibit the property of energy compaction. That means you can use only a small number of items, okay? For example, from 0 to 20, not from 0 to 255. Both of DCT and Hadamard have this property, this good property for using for comparison, okay? Beside a good quality. When we repeat the experiment for the non-ordered, that slide was for ordered Hadamard. Okay, when repeat for non-ordered Hadamard transform, we observe that the cumulative energy function EI does not increase quickly towards its maximum value. That means original Hadamard isn't okay. Ordered Hadamard is okay. Okay? Not ordered Hadamard isn't okay. Ordered Hadamard is okay. That's right. On the contrary, it looks more or less like the straight line type of function with a moderate slope. We see in the next slide. To verify this observation, look at the next slide here. Non-ordered and ordered Hadamard transforms. Here is ordered, and here is non-ordered. Okay, the ordered transform Hadamard transform of, for example, image of cameraman. Okay, and this is non-ordered. Okay, you see here some, for example, here you see more variations, and you see here about small variations, maybe by eye. Okay, but here is none or not ordered. All of the areas is the same. Okay, but here EAI, the cumulative transform energy sequences, this item is for ordered Hadamard, and this item is for non-ordered Hadamard. صدا نیست خانم سرا، صدا نیست. صدا ما موجود؟ کسی سرا؟ If all others have the sound, you can go from the session and go back. Maybe your sound is okay. Oh, صدا خیلی خوب نیست. اور صدا خیلی خوب هست. عمولی صدا خیلی خوب هست. یعنی صدا خوبه. الصوت جيد or زين. Asked. Okay. Mrs. Sarah said, my thought, okay, صوتي isn't okay, but for example, Mrs. Dalal said, my thought or صوتي is okay. But each of you, for example, Mrs. Sarah, has some errors. Please go out from the class and quickly go back. Maybe your problem is solved. That's right. And this is the last slide. This is the last slide for DCT and for Hadamard and Marsh transform. In the next session, we go for another transform. Okay, and after it, we go, for example, for histogram. Okay, this is the next slide, 33 of 33. That's right. You see here EAI for ordered transform and EAI for non-ordered transform. Okay, which is better? This is very better. This is very better. Okay, a small value of I, this horizontal axis is I, this vertical is EAI. Okay, as the last slide. For a value of I, you almost are reaching to the, for example, 100% of energy. Okay, for example, by selecting this item. What is this item? For example, 50 items. Okay, but here in non-ordered, for example, you choose, for example, this item. What is this item? This item is about 200s. Okay, that means non-ordered is very bad. It's very bad. Ordered version of, for example, Hadamard transform or Marsh transform. Okay, but this is very highlighted in Hadamard transform. The differences between ordered and non-ordered transforms. Okay, and this one, the sequence of transform as a function of the sample index. Okay, the I is increasing, the frequency or the frequency is increasing as a low slope. Okay, that's right. This is the last slide, and in the last session we have another concept. For example, maybe another transform. Okay. Be ready for starting some exercises. For example, working or executing some projects or exercises in MATLAB. Maybe from the next session. Okay, as this slide, maybe for example, at this slide, for example, maybe we say compare DCT and ordered Hadamard for a special image, and calculate the EAI and report that how many percentages of, for example, the original power is kept in the selected image. Okay, this item, you can run this item and implement this item in, for example, MATLAB. That's right, but not dormitory in this session. Maybe in the Wednesday. Okay, that's right. Is there any questions? Mr. Abbas, Mr. Ahmed Qasim, Mrs. Dalal, Mrs. Denam, Mr. Ahmed, Mrs. Lobna, and Mrs. Zainab, and Mr. Ahmed Zahrawi, and I don't see Mr. Uday. There isn't any question? Maybe there isn't, inshallah. Allah ta'ala ta'atukum bima salama. Okay? That's right.